Ni hao. Today we will be talking about triple integrals. The good news is there's not really that much to say, because if you understand double integrals, then you pretty much already understand triple integrals. A triple integral takes a form like this, where we have a function of up to 3 variables, and we integrate over some region that lies in R3. Maybe R is some solid blob like this. It is at any rate a solid, something that varies in 3 dimensions, so not simply the surface of the blob, but the interior as well. And the meaning of such a triple integral is exactly what you'd expect. It's exactly what an integral always means. It represents a weighted sum of infinitesimals involving the usual process of disintegration and reintegration. The disintegration is when we imagine taking our region and breaking it up into infinitely many, infinitesimally small, 3-dimensional bits, like this little infinitesimal bit of volume. It is not easy to draw a whole grid of them, but you can imagine lots of these little boxes stacked up in all 3 dimensions. Each little box corresponds to an infinitesimal bit of volume, dV, and our region R is filled with such infinitesimal boxes. What the integral is telling us to do is to go around to each one of them, take the volume, dV, multiply it by a certain weight, namely the value of the function at that point. Do that at each spot in the region, and then add up the results. That is what we mean by the triple integral of that function over that region. For example, let's suppose that this region represents some kind of a solid, and we have a function delta that at any point x, y, z in the solid gives us the solid's density at that point. Maybe we'll say it's measured in kilograms per cubic meter. Well, if that were the case, what would it mean to take this density function and to do a triple integral of it over the region? What would the physical significance of such a triple integral be? Well, that's easy to see. The triple integral is a sum, but we just want to think about the meaning of each one of the little terms. Well, each term is a product of 2 things, density and volume. The volume of that little infinitesimal box within the region, and the density at that point. Well, since this is supposed to be infinitesimal, there's no room for the density to vary. We can assume that the density is effectively constant throughout that infinitesimal box. And a constant density times volume gives us mass. That means that that product right there, those little things we're adding up, represents the mass of that little tiny infinitesimal bit of our solid. And if this thing represents the mass of a little bit, and we're adding all of those masses of the little bits up, what we end up with is, of course, the mass of the entire solid. And this would be in kilograms, since our density function was in kilograms per cubic meter. Triple integrals can arise very naturally in physics, since physical objects are, after all, 3-dimensional, and we can think of physical objects as being made up of lots of little infinitesimal pieces. If we want to understand, say, the gravitational attraction of this blob on some other blob, well, strictly speaking, we have to think about how every point in this blob is attracting every other point in that other blob. To understand the net effect, we're going to have to think about each possible attraction and add them up. Well, that adding up is a matter of integration. Anyway, that sort of fun can await you in your physics classes. Here, I just want to make sure you understand the meaning of a triple integral as a weighted sum of infinitesimals over some 3-dimensional region, and to give you a little experience actually computing a few. For the most part, everything you learned when studying double integrals carries over into this context, though by throwing in one more dimension, there's a little more room in which to get lost. But that shouldn't happen if you keep your wits about you. You'll remember that double integrals were easiest when we were integrating over a nice rectangular region, and by analogy, triple integrals are easiest when we are integrating over a rectangular box. For our first example of a triple integral, let's integrate this function, a pretty simple one, even if it is a function of 3 variables, over the box 1, 2, cross 0, 1, cross 2, 4. And remember what this notation means. We've seen it in just R2, but you can guess what it's going to mean in R3. This is the rectangular box whose x-coordinates run from 1 to 2, whose y-coordinates run from 0 to 1, and whose z-coordinates run from 2 to 4. That region would look something like this. Now, to put this request in symbolic form, what we are looking for is this, the triple integral of the function over the region R, which is this rectangular box. The meaning of this you are well acquainted with. We go through all of the box, and at every spot within that box, we take that infinitesimal bit of volume, multiply it by the value of the function evaluated at that point, and then sum up all those weighted infinitesimals. How do we actually crank it out? Exactly as you'd expect. We take this triple integral and turn it into an iterated integral. To do that, we need a systematic way of getting to every point in that box. And we do that much as we did in the two-dimensional case. We begin by thinking of some typical point within the region, and then from that point, we are going to move in just one dimension. With triple integrals, I tend to prefer going in the z direction first. It often makes things work out nicer. In this case, it won't matter which direction we go in first, but I'm going to go in z first, just because that's my habit. So, from our spot, we're going to imagine just the z coordinate varying, so that we would go and trace out some little line segment running through our solid. And instead of doing our weighted sum throughout the entire solid, we're first just going to imagine doing it just along that line where just z is varying. And if we do that, if we're just integrating in that one dimension, then for each point on that line, I'd be evaluating the function, which would give me x squared y squared z, at whatever coordinates we happen to be at. Then I would multiply by a little tiny bit of length, a little infinitesimal increment, which would be dz. So now I have my infinitesimal and the weight I have attached to it, and I want to add all of those things up just along that line. So in other words, I'm integrating as z varies from something to something. Well, I know what it's varying between here. In this case, it's very easy. It's varying between 2 and 4. So those are going to become my boundaries of integration. And now I have my innermost integral in my iterated integral. This whole integral is itself a function of x and y, because I could have started at some other spot and gotten some other little elevator shaft running through that solid, or a different one over here. It all would have depended on the x and y coordinates. So I need to continue my integration process, because all I've added up is along one particular line in the z direction. I need to ultimately sweep out the entire solid. From here, I guess I'll go in reverse alphabetical order. Let's integrate with respect to y next. That would mean taking this line segment and sweeping it out in the y direction, like that. When I do that, I would end up with a cross-section of my solid, something like this. So we're integrating that thing with respect to y, as y runs from back here, where y is 0, to over here, where y is 1. So my boundaries of integration will be 0 to 1. Very good. Now I have two iterated integrals. And that is the result of summing up all of those weighted infinitesimals just on one of these cross-sections of the solid. If I had looked at some other cross-section and summed up all those weighted infinitesimals on that cross-section, I would get a different sum. So I must take this figure and move it along the x direction. Let it sweep out the rest of the solid. What I'm doing then, by letting x vary and adding everything up as I go, is I'm integrating with respect to x as x runs from 1 to 2. And now at last I have my iterated integral, packed 3 deep instead of only 2. Once we have our iterated integral, the rest is just mechanical. Our innermost integral is with respect to z. So when we integrate our function with respect to z, the first two factors just sit there, because as far as an integral with respect to z is concerned, those are constants. So the x squared y squared just sits there. The integral of z with respect to z is, of course, z squared over 2, and we're evaluating when z is 2 and 4. And I need to bring the dy dx along for the ride. Now when you evaluate this stuff right here, you're going to get 16 minus 4, 12, 6. So since that is all 6, let's go ahead and pull that constant to 6 through both remaining integrals. And now that we've done that, all the novelty of this problem is gone. This is just an ordinary iterated double integral, the kind of thing we have done many times before. I will leave the details of that easy calculation to you. When you do that, you should get 14 over 3. And so much for that integral. There are a few different things to think about here. First and foremost, being able to interpret the triple integral as a weighted sum of infinitesimals over some particular region of space. Second is the crucial idea that such a triple integral can be turned into an iterated integral, which is the sort of thing that we can actually compute. And third is the details of the computation itself. These can admittedly get a little ugly with triple integrals, but I won't make you suffer too much. Let's do another example where I start you off with an iterated integral, and we'll just run through the computation completely. Suppose we're given this integral to compute. A few things to notice. One, the function is not so nice as what we were just dealing with. It's not a polynomial, but it's still not too bad. And two, even though I gave this to you in the form of an iterated integral, you can see right away that the region to which this corresponds in R3 is definitely not a rectangular box. X is running from 0 to x equals y, which is a plane in R3, and then y is running from 0 to y equals z, which is another plane in R3, and z is running from then 0 to 1. As with the double integrals, when we have a triple iterated integral, the outermost integral is going to have to involve just constants, but the ones on the inside can involve the variables. Now, fortunately, I don't have to actually visualize the region I'm integrating over, since I already have it as an iterated integral. So let's get to work. Here is the iterated integral as given to us. Now I have to take it in the form that's given. If for some reason I want to switch it around and maybe do y first or z first, as I described in the last problem, I can't just do that. To switch the order of integration, I really would need to understand what the region looked like, so that I could then carefully figure out what the new boundaries of integration would be. Well, it's probably not worth it, so let's just see if we can do it as is. This innermost integral is with respect to x. So we're integrating this function with respect to x. Well, that is particularly easy, since as far as the integral with respect to x is concerned, this is a constant. Z and y are frozen. So it would be like if we were integrating the constant 7 over some particular interval. If we did that, the result would just be 7 times the length of that interval, which in this case would be y, because the interval is running from 0 to y. Remember, y is frozen as well. So if this were all 7, the result of that integral would just be 7y. In our case, alright, this looks a little more complicated than 7, but it still represents a constant as far as that inner integral is concerned. So that's the constant that we would multiply by the length of the interval, y. So the result of that innermost integral is simply going to be y times that constant function ze to the y squared. And of course I need to bring the dy dz down. And if by any chance that way of thinking confused you, you could always just do this a little more formally by saying an antiderivative of this function with respect to x would be x times ze to the y squared. And then you have to evaluate that when x is y, so it would become yze to the y squared minus 0 times e to the y squared, which of course would just be this. Alright, either way you do it, this is the result. Now we're on familiar ground again. That's one nice thing about triple integrals. Once you have done the innermost integral, you've turned it into something you're already a little more comfortable with, an iterated double integral. Let's carry out the details. We're integrating this thing with respect to y. Well, z is a constant as far as y is concerned, so when I do my integration, it can just sit there. In fact, rather than just letting it sit there, it might help if we think about just pulling that z through that inner integral. I can't pull it through the outer integral because that's an integral with respect to z. If I pull it through the inner integral, then the result looks like this. That's a little less intimidating looking, because to integrate this function with respect to y isn't hard at all. This cries out either for a formal substitution, where you would let this exponent be u, because then du would basically be the y dy, up to a constant anyway, or you just stare at it and think about it until the antiderivative occurs to you, making some adjustments as need be. Let's do that. The antiderivative is going to be something like e to the y squared. Will that do the trick? Well, if we take the derivative of this, do we get this stuff back? We certainly get e to the y squared, but when we use the chain rule, we're then going to get a 2y. Well, we like the y, but we don't like the 2. That means that we need to introduce a factor of a half to balance it out, so that when I take the derivative of this thing, I get this stuff times 2y, but that cancels with the 2, just leaving me with my target function. Now we have our antiderivative, and we know we're going to have to evaluate it when y is 0 and when y is z, and then do the usual subtraction. Oh, and we know that this constant factor of a half can be pulled through the brackets, and then once outside it can be pulled through the integral sign, so let's do that. That looks a little nicer. Now let's actually evaluate that junk. When we do so, we get e to the z squared minus 1. All right, now this integral isn't too bad. If we distribute this z through, we end up with two terms whose antiderivatives are easy. In fact, one of them is a function we already integrated up here. We've seen already that the antiderivative of that first term will be 1/2 e to the z squared. That's exactly what we did right here. As for the second term, well, of course, that's just going to be 1/2 z squared, and we have to evaluate when z is 0 and 1. Let's factor out that half and pull it through, giving us a quarter outside and this stuff inside. Now when we evaluate that, we get e minus 1 minus 1, so that the whole thing becomes e minus 2 over 4. And that's it. That is the numerical value of our integral. Okay, so I think you know what a triple integral is, and I think you have a sense that evaluating a triple integral is really no different than evaluating a double integral, just one more round in the proceedings. But I should give you an example to show some of what's involved in turning a triple integral into an iterated integral when the region you are integrating over isn't quite so nice as a rectangular box. For example, suppose our region is this hemisphere. And again, I mean the solid, the top half of this ball. And to be definite, let's say the radius is going to be 3. And suppose that we have some function of 3 variables, f of x, y, and z, and we want to integrate our function over this solid region. And our job is to express our triple integral as an iterated integral. How are we going to do that? Now, I've just let the function just be an abstract function f, because I don't care in this problem about actually computing the iterated integral once I have it. I'm just interested in the process of turning this into an iterated integral. So the nature of the function is really immaterial. And again, we already know what this means. We're going through this solid region at every little spot. We're taking an infinitesimal bit of volume, dv, weighting it with the value of the function at that point, and then adding them all up. So we know what it means, we know what's involved in evaluating an iterated integral once we have one, but we just want to come up with the iterated integral. How are we going to do that? It's the usual game, and we did this once already with a rectangular box region. We imagine a typical point somewhere inside the region, and we are going to sweep the whole region out one dimension at a time. So as I said before, I think it's much easier to follow when you do z first. So imagine from our typical point, we're going to just let z vary. We're going to keep x and y fixed. If we do that, we're going to get this little line segment from the floor up to the top of that hemisphere. And at every point on that little line segment, I'm going to be multiplying the value of the function by a little infinitesimal bit of length, because this is only varying in one dimension. So I would have something like the value of the function times dz. That would be the thing I would be integrating in my innermost integral. And I'll be integrating with respect to z as z runs from down here in the xy plane up to this hemisphere. Well, in the xy plane, z, of course, is 0. But what's the value of z going to be when I hit the hemisphere? That is going to depend on my x and y coordinates of where I started. So this will be some function of x and y. What will it be? Well, that's not too hard. We know the equation of the sphere, of which that hemisphere is the top half, namely x squared plus y squared plus z squared is 9. If we solve for z and use the positive square root, we're going to get z is the square root of 9 minus x squared minus y squared is the equation of that hemisphere. So that means my upper boundary of integration, the value of z at which I'm going to stop, will be precisely that, square root of 9 minus x squared minus y squared. Good, that is my innermost integral. Now I'm going to have to move on to one of the other dimensions, x or y. I'll take it in reverse alphabetical order. I will integrate next with respect to y. So instead of just having that right there, what I'd get, for example, that one, and that one, and that one, and so on and so forth, until I end up with everything on that green cross-section. I've summed up everything here, and 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 here. I've got all those weighted sums. And I get that by taking this, which corresponds to the blue stuff, and integrating with respect to y, as y runs from whatever the value of y is here to whatever the value of y is here. Ah, but those values of y depend on the particular frozen value of x. Because if x is all the way out here close to 3, y is not going to vary as much. If x is down here at 0, y is going to vary between -3 and +3. So these boundaries of integration are themselves going to be functions of x. So I have to think about how x and y are related just on that circle, since I've already taken care of everything in the z direction. Well, that circle is centered at the origin with a radius of 3, so of course its equation is x squared plus y squared is 9. Or in other words, y is plus or minus the square root of 9 minus x squared. So that gives me the answer I want. All this green stuff takes place for some fixed value of x. For that particular value of x, what are the values of y that it's running between? Well, there they are, because they're points on that purple circle. If x were very close to 3, then I would have a very small range of possible y's, since this x squared would be very close to 9, and this would be a very small number. Anyway, I now know the boundaries of integration on my second integral, on my middle integral. I'm going to need a little more room, it looks like. That's better. The boundaries on that integral will be from minus root 9 minus x squared to positive root 9 minus x squared. And once again, this innermost integral represents the sum we get when we add everything up along just that blue line. What I'm doing now is taking that blue line and sweeping it out in the y dimension, hence this second iterated integral. And the boundaries are functions of x because the starting and stopping places will vary depending on the frozen value of x. They'll be smaller somewhere else and larger in other places. Okay, so this gives me my weighted sum of infinitesimals across an entire cross-section. All I have to do now is move this cross-section in the third and final dimension, the x dimension. So I'm going to integrate with respect to x as x. And note I don't need to leave much room here because the outermost integral is always between two constant boundaries. X is going to run from -3 to 3 because I'm getting my sums on little chunks like that, or that, or that, small or large, as I sweep that green cross-section across the whole thing, starting somewhere back here where we can't see, where x is -3, all the way here to where x is 3, where that little semicircle collapses into a point. And that's it. That is our iterated integral. So it's the same old process of making sure we sweep out the entire region over which we're integrating, one dimension at a time. Definitely trickier in 3 dimensions than 2, in part because it's harder to draw the region, and you definitely need a good picture to set up those boundaries of integration. A few last thoughts. First, some of you probably are wondering whether there's some analog to polar coordinates in R3 that might make this easier, since the region, after all, is nice and circular. It's very much like the kind of thing we would do with polar coordinates in R2. The answer is yes. In fact, there are 2 such alternate systems of coordinates that can be used in R3. The cylindrical coordinate system, which is a direct extension of the polar coordinate system, and the spherical coordinate system, which has a few quirks of its own. You'll meet both of them in the next video. The other thing I want to mention is really just a reminder, but an important one. When you first met integration in a previous class and you worked with functions of one variable, you saw that you could always interpret definite integrals as areas under curves, like this. Similarly, in this class, when you had a function of 2 variables, and we integrated such a function over some region in the xy plane, we could think of that double integral as representing the volume of some chunk of space under the graph, so that this double integral corresponded to the volume of that thing. But I urged you in an earlier video not to automatically think of double integrals as representing volumes, just to think of it in terms of the domain, going through that region of integration, taking all those little infinitesimal regions, attaching weights and adding them up, just thinking of it as a weighted sum. I mention that in part because of the kind of thing we were talking about today. When we are looking at a triple integral, it doesn't correspond to anything geometrical, or at least nothing that we can get our heads around. Yes, strictly speaking, it corresponds to some sort of hypervolume in R4, which is a great and useful thing to know if you are a four-dimensional creature, because then you can relate this analytic stuff to geometric stuff. But if you are three-dimensional, as we are, alas, it really doesn't help to think that way. And sometimes people get confused and think that when you are doing your triple integral over some region, some chunk of R3, that you are somehow asking for the volume of that chunk. You are not. That chunk is just telling you what your region of integration is. The only way you would be looking for the volume is if your function is just the constant function 1. It's true that if I have some chunk of R3 like this, let's just call that R, and I wanted to integrate not some genuine function, but rather I just integrated the function 1, which of course I wouldn't write that way, I would just write it as the integral of dv. It's true that that triple integral I actually can relate to a volume. The value of that triple integral is actually equal to the volume of the region, which you can see just by thinking about what it means. This is telling me, go through this region, and at every little spot, every little infinitesimal bit of volume, attach a weight to that volume. Well, what weight am I attaching to it? The only weight I'm attaching to it is just the number 1, so I'm not really attaching any weight at all. So my weighted sum of little volumes really isn't a weighted sum if my triple integral is like this. My weighted sum really is just the sum of all those little dv's, and when I add up all those dv's, all those little bits of volume, of course I just get the volume of R. So yes, there is a relationship between triple integrals and volumes, but it's not a very exciting one at all. It's not, I suppose, without its uses, but in general, when we're doing a triple integral, we're actually integrating a legitimate function. We're not integrating the constant function 1. You want to break that connection in your mind between integrals and volumes, areas, and so on and so forth. Or I shouldn't say break it, because it is a useful connection, but don't attach too much weight. The primary interpretation of any integral is as a weighted sum. Okay, that's enough. Until next time, 再见.